always love to talk after lunch because my research is about food and agriculture, and so typically I can relate. And I can give you many examples of what you have eaten and how they've been processed and how nanotechnology enables the food and agriculture business. But today, we're not here to talk about me. Today, we're here to talk about climate resilience and how nanotechnology can support a society that is more resilient to climate change. And we have three amazing speakers. Like, these are really, really good top-class speakers. So I'm very happy that they join us and they're going to talk about the research. Before doing that, though, I would like to give a mention and further resonate the speech that President Corbett gave this morning about the importance of innovating in climate, and particularly she started as presidential initiative the Climate Project, which I'm part of. And really the Climate Project is a brand new initiative that she launched, and the idea is to convey all the faculty to work together to have an impact on climate and also energy, of course, with the idea that we're going to have a tangible impact on the trajectory of climate change in the next 10 years. We cannot do it alone, and so what the Climate Project wants to do is really to leverage all the different entities that are already part of MIT and to work with them so that the faculty can work to innovate in climate. And particularly, we see the project as an ecosystem for innovation in deep tech. So we really want MIT to become the hub that puts together industry, incubators, investors, foundations, the startups that come out of our university together with the government, national lab, and other university partners to work together to innovate in the realm of climate. As you may know, innovating climate is extremely difficult. The economy is developing. There are no real models that can be used, particularly for some technologies. And so this ecosystem for innovation would particularly be focused on innovation at scale. And it's very interesting because we talk about this at the Nano Summit, and Nano is 10 to minus 9, as you know. And for climate, we need to go 10 to the 9 and up, right? So we need to cover 18 order of magnitudes, even 20. So that's really the beauty, the challenge, and the opportunities that we're having. And we really, really need to work as a whole to solve this problem. The vision is summarized in the well-being of humanity and prosperity of humanity. And to do that, we need to take care of ecology, health, mobility, the built environment, food, energy, policies, and trade and industry. And so really putting this at the center of innovation of campus and thinking about these topics as interconnected topics to have a positive impact on our climate. The Climate Project is organized in different key areas, and we have 6 faculty leadership, and as you can see, I'm one of them. And particularly, I'm leading an effort that is called the wildcards, which are high-risk, high-payoff projects that, if successful, can have a big, big impact on changing the trajectory of climate change, but of course, they're also high risk. As area of interest, we have decarbonizing the energy and the industry, empowering frontline community, which are going to be the one most affected by climate change. We need to redesign resilience at prosperous cities. We need to enable new policy to be able to translate. And then we have a focus on science. So what's the science that interests the atmosphere, the land, and the oceans, and then, of course, the wildcard that I just discussed. One of the help that we want to give to faculty through the Climate Project is to assess priorities, identify gaps in knowledge and technologies, and then put several faculty together in a DARPA-style program that can be launched and that can really make an impact on the technologies. We also support cross-cutting research among different missions. Particularly, we recently launched 2 projects, one on sense, share, and understand climate, and one related to heat stress and cooling. And I just want to thank you for your attention, and I hope you're going to enjoy the next 50 minutes or so. And I please welcome to the stage Professor Michael Strano, who's going to give us his talk. Thank you very much, Michael.
Thank you very much for that introduction. I have it's my pleasure to speak to you on this topic of nano and climate resilience. I'm a professor in chemical engineering. I've been here about 17 years, and I lead a nanotechnology laboratory. And I'm pleased to be here. I thought I would start off. Why are climate problems? Why can they be solved by nanotechnology? So nanomaterials give us new ways to control catalysis and reactivity. So many climate problems are really chemistry problems. And at the nanometer scale, we can design new catalysts that can do transformations, that can do things like react greenhouse gases to useful properties. And then climate problems also intersect with energy conservation and how we use energy. And nanomaterials give us new ways to manipulate and control the way energy flows, like through carbon nanotubes and nanowires. And many climate problems involve our need to separate and sort and to process molecules. And we have new ways using nanopores that we can manipulate molecules for that purpose. So what I thought I would talk to you today about are three projects from my laboratory where we're applying nanotechnology solutions to longstanding climate challenges. The first addresses how do we valorize or make useful waste methane and urea. And you'll probably the pioneer who will speak next in this area has been Desirée Plata, who's pointed out methane is a very potent greenhouse gas. Also, chemistry-wise, it's actually notoriously difficult to react. And so it's responsible for 0.5% of warming. And so we want to do something with waste methane. It's produced from the decay of biogas. And there are many social sources of waste methane. At the same time, we have an industry where we purposely make urea, and we make it from ammonia from the Haber-Bosch process, a very energy-intensive process. But at the same time, actually in wastewater, we have enough urea to actually supply the whole economy. And so we see this as a wasted opportunity. We've been working on chemical ways to react methane in water with urea. A big breakthrough in this space we published just earlier this year. We made what we call a synthetic methanotrope. Like what nano allows us to do is to basically do what nature can do with bacteria, but in the form of two different nanoparticles. A ZSM5 is an aluminosilicate nanoparticle, and it'll take methane and it'll react it to methanol, which now you can go and make useful products with. If you use this enzyme called alcohol oxidase, which we also mount on a nanoparticle. Well, this will actually couple back and will feed the ZSM5 an oxidizer. And this kind of chemical cycle is what you would find in a living organism, but nanotechnology allows us to actually replicate it in test tube and replicate it into a larger reactor. And so this does what bacteria can do in water. It can take methane and it can make a useful intermediate. And what we've been doing is using this chemistry to capture the urea in wastewater. And this is opening up a new synthetic pathway where we can take waste methane, waste urea, and then make a variety of renewable materials like adhesives, green insulation, materials for sustainable construction, and even fertilizer. So if you're interested, please learn more. You can go to my website and other resources. We're very excited about that. I wanted to move on to the next topic. These are new materials that we just invented in the lab, and they can solve the problem of infrastructure for the hydrogen economy. So hydrogen is the fuel. The growth of hydrogen as a fuel, we have to make the transition to it. It's a perfect fuel. It burns to water, and it's going to be very important for sectors that are difficult to electrify. And so there's substantial growth in the hydrogen economy that's predicted, but there is a drawback. Maybe few people in the room know that you can't just put hydrogen gas into our natural gas infrastructure. It would be nice. There's an insidious engineering problem that happens. It's called hydrogen embrittlement. Hydrogen is so small as a molecule, it'll actually intercalate even the strongest steels. And when it does so, it turns the steel into basically fragile glass. And the way you know it happened is there's an explosion. So this problem really needs to be solved in order to transition to the hydrogen economy. And so we, a few years ago, we invented a completely new class of materials. It's a 2D polymer. This is called a polyaramid. It's one of the strongest polymers ever measured. If you're familiar with Kevlar and a bulletproof vest, it's a similar chemistry, but actually we solved the problem of polymerizing in 2 dimensions. And what we've made is a very interesting material. It's a polymer, we would all agree, the chemists would agree, but once we actually spin it into a film, it makes a very tightly bound, hydrogen-bound film that starts to look like graphene. It's a spray-on or paint-on strong, durable graphene. And I think science has never seen anything like it. It forms these very tightly bound stacks. And what we found is it's the first impermeable paint-on polymer. Actually, we measure no gas permeability through it at all. This graph, permeability is measured in this unit called Barrer. All conventional polymers are up here. This polymer is not even close. It's orders of magnitude lower. It's actually at the detection limit. You really can't detect any further. And the only other types of materials that have this property are like graphene. So basically, we have a paint-on perfect barrier material, and this graph highlights how unusual this material is. It's a polymer, but you paint it on, it becomes like a perfect crystal graphene. And so we're using this to solve the problem of hydrogen embrittlement. Please go to this QR code. You can find out more. We're very excited to talk to you more about that. And then just really quick, in the last minute or so that I have, we're also working on technologies that can enable the 4th agricultural revolution, and we're using pioneering plant nanotechnology. The problem here we're trying to solve is global food prices are rising. They're rising for a variety of reasons, but one is that climates are changing, and there's examples of that all over. The palm oil that we get on our shelves, a lot of it comes from Malaysia, and if you look at the rainfall, it's just consistently falling. The climate is changing, and at some point where we grow things, we'll have to find alternatives to how we grow the foods that we take for granted. In the meantime, prices are going to rise. So this is definitely a climate problem, and it's contributing to global food insecurity. What my colleagues and I made an entity called DISTAP. It's MIT's research enterprise in Singapore through the SMART program. It gives myself and also our chair, Benedetto Marelli, a vehicle to work on problems like this in agriculture. Briefly, what we're trying to do are make tools that could close the loop and be able to grow crops. If you think of the input, light, water, CO2, and fertilizer, if you think of those as inputs, you could imagine nanotechnology-enabled tools which give you feedback from the plant that allow you to do rapid feedback control and make technology where you could essentially grow anything. And so go here to this QR code, and you can find out more about our pioneering work. I'm interested in hearing from the other speakers, so I'm going to end there, and I'm happy to pass it off to the next speaker. Yeah. I think we're going to take questions at the end, right?
I'm Desirée Plata. I am a professor in civil and environmental engineering, and I don't have a single SEM today, so I'm going to apologize to Vlad personally, but we have them. I'll show him after. So I want to start by talking about sustainable innovation and the role that it has in the restorative economy. The economic systems that we have today are depleting to our resources, inherently polluting, and all of that is an externality that's not accommodated in the business model. So I'm going to take you to that macroscopic scale that Benedetto mentioned, and then drive back down to the nano scale. One thing that I want to underscore here, for those of you who aren't aware, the Climate Project at MIT has an articulated mission to change the trajectory of global climate outcomes within a decade. And this is what that trajectory looks like. It looked like this 5 years ago. It looks like this today. Our global anthropogenic CO2 emissions are around 51 gigatons annually. Oops. Excuse me, and implemented policies have some ability to tune those total emissions, but in order to hit any kind of 2-degree warming targets, we have to fundamentally change the way that we do things. I have a list of technologies that I think are must-haves in order to meet this goal or bridge this gap. It includes things that are being worked on in the Climate Project, like better adaptation and resilience, smarter cities, nuclear energy for data centers and manufacturing, electrification, including systems integrated in the materials that we need for electrification, industrial heating or transportable liquid fuels. Sustainable agriculture is enormous and must be addressed. Today I'm going to focus on biological carbon removals and the associated bioeconomy that would need to come along with that to finance the whole thing. Now, in order to hit that 2-degree line, the IPCC estimates that we need 10 gigatons of CO2 removal by 2050. Now, 10 gigatons is bigger than the coal industry itself, and that's a rock. So we're talking about pulling a gas out of the sky, a dilute substrate. That's hard. This industry had 100 years to scale or more. We've got to do this in a couple of decades. One of the only places on Earth where we move that amount of material is actually in the agricultural sector. So the dry weight of the agricultural sector is around 18 gigatons, and the residues or waste associated with that are on the order of 4 to 7 gigatons of dry waste. So we like to call the agricultural biosphere the sleeping giant of carbon removals that hasn't really necessarily gotten the attention that it deserves. And if you do this accounting, there's somewhere approaching 7 gigatons of CO2 equivalents removable available on the face of the Earth today. Now, about 1.2 of that could be readily used. It's either directly incinerated back to the atmosphere or it's left on the field. And you have to leave some of that carbon on the field. I want to be clear and fair there to keep the soil healthy, but you can remove a fraction of it. And we're estimating that that's around 1 gigaton of CO2 equivalents. Food waste amounts to around 1 gigaton per year CO2 equivalent removal. So if you don't have composting in your town, get that quickly. I want to walk through why the financing of this system becomes really important. How many people have heard about direct air capture? Right, so you're pushing air through fans, removing that 420 parts per million CO2 as it comes through. Direct air capture carbon credits sell for around $900 to $1,200 per ton CO2 equivalent. Now, if we want to hit that 10 billion metric ton mark, we're going to be spending half of US GDP to do it, right? It's completely intractable. Not to mention the fact that direct air capture would top out around a gigaton of removal if we made every air handler we ever made 80 times over. All right, so let's just do what we did 80 times again and see how that helps us out. It's not a great move, right? So the global GDP is around $100 and $110 trillion, US GDP around $25 trillion. If we start to look at bio-based storage technologies, we think those can happen around $100 to $150 a ton CO2 removal. The methane emissions reduction credits are on the order of $25 a ton CO2 removal, and that's pretty exciting. And just for reference, the value of our emissions, so if you take the total global economy and divide it by that 51 gigatons of CO2 emissions, you've only got about $2,000 to play with per ton of CO2 that we emit. So nanomaterials and specialty chemicals occupy a unique place in the market. If we look at the way a barrel of oil is used today, the value that's derived from specialty chemicals is on the order of the value that's derived from the fuel itself. So if 76% of the volume of a barrel of oil is going to products that we actually just directly burn, that generates almost $1 trillion. In equal proportion, financially is the 16% of specialty chemicals. So there's a lot of revenue moving around in the specialty chemicals market. Now, how could we possibly take advantage of a similar system for a carbohydrate economy that's built on biomaterials as opposed to petrochemical hydrocarbons? How would we understand the complexity of what nature is doing in a way that we can manipulate that matter on the nanoscale ourselves? Would we be tolerant to the product distribution that nature is? Not every leaf is the same, of course, but it works perfectly well. How do we reconcile the need to pace innovation at a level that allows us to incorporate environmental objectives into the design process, along with traditional performance and cost ones? So the example I'm going to tell you about today is derived from ocean plastic waste. And what I love about ocean plastic waste is that it's wonderfully photogenic as a pollutant. This brought a lot of attention not only to the dissolved chemicals that we've been floating in since the 1970s and 50s or sooner, but it also brought a lot of attention to climate change. We can't grab CO2 in front of us. We can't take a picture of it and put it on Instagram. But plastic pollution has brought an immense amount of attention to these global scale problems. Now, what you might not know is that plastic production in the next 10 to 12 years is going to outpace the integrated production since plastics were invented. So if you think this problem is bad now, it will double in your lifetime if we don't change how we're doing things. So we started to look at those transformation processes that occur between the nanophase plastics and the small particles that are formed and the dissolved molecules. And we can actually pair those transformations together, much like you would a social network, who's friends with who's turning into what. And we can zoom in with chemical molecular specificity. So not only can we know which molecule is parent molecule is becoming which child molecule, but how that transformation is occurring. And something that is important to point out here is, one, degradation is not monotonic. It doesn't just fall apart, it forms other things. But two, that this is an incredibly data-dense network. This is high throughput experimentation in one pot. So if we can trace these complex networks, every one of those nodes is a molecule, every one of those edges has a reaction rate associated with it. This is how we generate big data. This is how I get molecules to carry cell phones in their pocket and tell me everything they ever bought and where they've been that day. So I'm pretty excited about that. We've applied this technology to several different common industrial chemicals, polymers here, polyamide 6, polycaprolactone, which is in your medical implants, and polylactic acid, the greenware. I won't get into the details of this, but functionally we can start to ask the question, if we just mathematically multiply n there, the number of units that we're adding together, and ask what's left over, we can start to identify related groups of molecules, so subsets of molecules that are all interrelated. And as we grow those molecules, their retention time changes on this instrument in a very logical way that actually tells us how it will behave in an environmental system. Will it stick to a particle? Will it go into your cell? And what have you. And we can also know something about the chemical structure based on how it behaves in response to changes in pH. Now, we can take that and extend it to systems in the natural world, including biomolecules that are present in the ocean. So in this particular example, we suspended a complex polymer, enriched bacteria that were able to colonize that polymer, and started to systematically study which bacteria and what proteins in their genetic makeup were able to perform which chemical transformations. Now, this is a different experimental set, but functionally what we can now try to do is step through the biological molecules, which are all linked through that intellectual exercise that we do in the data. Those are the red symbols, and the biomolecules, the gray ones. So we know who's turning into what, we know what came from an industrial material, or maybe that's your desired product in this case, and what came from the biological exudates themselves. Now, if we were going to really start to understand how nature was performing biotransformations in these complex mixtures, we would have to amass a lot more data than what I'm showing you here. So high throughput experimentation is truly necessary. Those complex molecular networks exist in every one of the examples here that I'll tell you about. So Professor Brad Olson's group in chemical engineering has synthetically made over 700 different polymers. I think this is the world's largest synthetic heteropolymer library. We subject those to high throughput degradation testing along with high throughput material performance testing, right? Nobody likes a paper straw We want these materials to be good at their primary job, in addition to being compatible with the environment. And then we can use that chemical transformations data en masse to understand what gives rise to biodegradation and how can we manipulate it using the tools of biology. This is just some SMILES code, or big SMILES as we call it in polymers. It's a line entry system, so your computer can understand what the molecular structure is. And we can start to understand how chemical structure imparts a particular reactivity or desired biological output. This is available to you in Crypt app, which is just publicly launched. So it's all that cool materials performance data, the biodegradation data, along with performance and cost metrics, to really start to change the way we design materials and processes so that they are implicitly more compatible with the way the Earth system works. So I'll end by saying that nature's works symbiotically and restoratively. The materials and energy fluxes are locally balanced. Our economic systems haven't done that very well. Prosperous nations tend to emit 20 tons of carbon CO2 equivalents per person per year, whereas transitioning nations emit 10 times less. The only way you move between these lines is either with substantive investment in a decarbonized grid or renewable energy, or through geopolitical restructuring events like war. The goal here is to use sustainable design to move us down these lines and not enormous global conflict. And that's really what's at stake here. This is an all of MIT effort in order to transition the global economy. Now that's improbable, but it's not impossible. So I'd like to end with a little homage to the improbability walk behind MIT.nano. This was the brainchild of Vlad as to honor Millie Dresselhaus, the queen of nanocarbon. And Millie used to say that her path from being the daughter of a Polish immigrant to an institute professor at MIT was highly improbable, but importantly, not impossible. The same is true for this challenge.
As it comes on. Oops. Okay, can you guys hear me? All right, thank you. Thanks for having me, Vladimir and Benedetto. So I'm going to talk about I'm going to talk about what we are doing in my lab. We work on advanced materials and interfaces, and interestingly, they go across climate to health. And in fact, a lot of the climate problems impact health. And I'll highlight two things we are doing on carbon capture and in agriculture today. So as you already heard, the carbon problem is a gigascale problem, and for us to be able to remove so many gigatons of CO2, we need to be thinking about scale from the get-go. And as was highlighted before, there are many scales here, and we need to go to macro scales, but using really nanoscale effects, because surface to volume ratio plays a very, very important role. And if you look at the whole carbon problem, it's really a CapEx, OpEx problem. And how do we kind of solve this CapEx, OpEx problem has been at the heart of a lot of the things that we've been working on. And then if you go to renewables, you need storage. Otherwise, it's hard to transition. And while I'm not going to cover this today, but we've been working on non-lithium, non-flammable batteries. It's been commercialized by a company where I co-founded called Alcim Energy. And we hope to put things out into market in maybe 2027. But it's really kind of closing these loops will help us to do the energy transition. So let me kind of jump into the CO2 capture and conversion and thinking about this at scale from the get-go. And we've been looking at different sources of CO2, whether it's point source all the way to DOC and DAC. So these are oceans where you have CO2 concentrations that are 100 times more than in air. So it's more concentrated, so you can process less volumes. shockingly the same concentration as you would see in the exhaust of a gas turbine. So ocean acidification effects are already having a big impact right here, next to us in Maine. So I'll talk a little bit about that. And then how do you capture and then valorize that CO2 so that you can make something that's economically feasible? So if you look at our conventional sort of ways to do capture and conversion, you're going, the capture step is, if I draw here, there are no numbers here, but it's cost versus energetics. The cost to capture is, the capture is driven mostly by kinetics, so it's a capex problem, and then you need to extract, and then you need to do something with it, and you now start to add a lot of energetics. But if you're able to actually go and integrate a number of these components, for example, instead of doing extraction, you do direct conversion, then you can have a lot of savings, and those are the kind of system-level architectures that we are also been implementing. So an example I like to start off with is the Petronova plant. If some of you have known or seen these, this is it took 500, where is this going? Yeah, it's a $500 million capex plant, and it's about the size of this Prudential Tower, uses amines to capture CO2, and where the solubility of CO2 is pretty high. But so one of the questions I had was, why do you need such large towers? And we started looking at some of these things to optimize this. And actually this went out of business when oil markets crashed because the CO2 was used for enhanced oil recovery here. So if you kind of look at this, these are all packed bed kind of reactors, and the absorption rate is controlled by film thickness, which is on the order of hundreds of microns. So the thought was, okay, how do I increase surface area? I could go to finer and finer drops and create finer and finer mists, and you can now significantly increase sort of that surface to volume ratio and go to large capture and significantly reduce the capex and cost, etc. The question is, okay, why didn't anyone do this? Because you mist get entrained, and you can go out. If you look out there, you can see a bunch of that plumes coming out of cooling towers there. You can see a plume right there. So we have solved this problem before, where we have invented a technology where we sort of inject these plumes with electrical charge, and when you switch on, we can sort of capture that. And this has actually been commercialized now with where I've taken this out through a company called Infinite Cooling, and we demonstrated this at scale actually at MIT power plant here. So if you take something like that and we are combining that with our carbon capture mists, we can significantly reduce capex costs and then bring this down. And we've actually proven this out for cooling towers, and we can bring this to bear to some of these absorption towers. So this is actually a prototype that went from lab, the one that I just showed you, which was a coffee strainer, to the MIT cooling tower, all the way to now industrial cooling towers, and now being deployed at EDF, where we've now modularized this to do industrial cooling tower capture. But then we are using these technologies and putting them together to really think about absorption towers in a totally different way, and kind of scale, make them more efficient and reduce the capex costs. The other, another interesting challenge that came up was in all of these capture systems, you have some sort of an absorber, right? Like the hydroxide solutions that I showed you. And then you need to then release the CO2 or do conversion of that CO2. And these are both at odds with each other. And that's because what happens is the absorption here and the conversion leads to, when you want to do absorption, you need hydroxides to be there. And when you are doing conversion, you want everything to go into a carbonate. And what happens is you end up somewhere in between. And so the higher the carbonate loading, the worse the absorption is. And then, or the higher the hydroxide, when you come into the conversion part, you're essentially protonating this, so you create water. So you want to make sure that you get complete conversion, but most of the times you're not, you're sort of in this 50-50 kind of a range. So one of the things we did was, how do you solve this constraint? You're in the absorption, you're in this corner. Ideally, you want to be here when you're doing conversion, but you end up sort of being here or in that extreme. So you want to kind of create some black box here that's going to decouple these two systems. And what we did was so that you can then have something that does the absorption and then something that does a conversion. So the way we did this was using nanofiltration, where you can now separate the carbonate and the hydroxide ions in a way that you can now create a system that that basically uses the hydroxides here for the capture, and the conversion is purely on the carbonate solutions. And this was extremely effective. We've gotten a significant boost in the cost reduction, but also operational stability and operational window for both the capture and release kind of steps. So my kind of goal is putting all these together. We have had few other nice inventions here on looking at conversion and scaling conversion using hierarchical gas diffusion electrodes. And so I start with my source, do this sort of a capture, and then using some of the electrochemical reduction steps that where we've shown using these hierarchical conductors to scale, we can actually then regenerate our sorbent and bring it back. And so this kind of overall cycle could really reduce both CapEx and OpEx and increase the operational stability of these kind of systems. So I'll quickly step to another side of the story, which is oceans. Right? So about 30% of our emissions partition into the oceans, leading to increased ocean acidification. And but the interesting thing is the oceans are the biggest contactor there is, and you have about 100 times more CO2 in ocean captured than in air, and therefore the capture step is kind of already done for you. So what we have done here is using a process where we electrochemically convert the bicarbonate into molecular CO2, which could be stripped off, and then regenerated here where we deprotonate and can release alkalized water. We've been able to get this with some of the lowest energetics per ton of CO2, no membranes, and we could create these nice effective alkalized ocean streams. Yeah. I'm sorry? What?
We store living coral reefs all around the globe.
Yeah.
The carbon dioxide capture would be tenfold what it is now.
Sure. Okay. So what we are doing is we are trying to extract that CO2 out of the oceans, and these could be deployed in offshore systems or in with shipping and others. And one interesting application for us here is in aquaculture, where ocean acidification effects have really sort of diminished the carbonate that is needed to actually form for shellfish to form shells, and is a interesting market where the specific value of the CO2 removal is quite high. And in fact, there's been a loss of productivity in Washington oyster kind of market, as well as in U of Maine, where ocean waters are artificially buffered today. So we are using this as a opportunity for us to show that you can actually do this capture and have impact on coastline communities as well as local economies, and create a local economic case for this problem. So the way this is done is we are partnering with U of Maine, and this is aragonite supersaturation as a function of pH. So there is a window where we can optimize these waters. Today, they actually buffer the ocean water artificially to be able to grow these shellfish. So we are scaling up our technology, and what we have done here is already shown with U of Maine that we can actually apply our buffered waters. So we are electrochemically removing the CO2 and taking these alkali streams that we are creating, and is already we demonstrated that we can, instead of artificially buffering, we could sort of do it this way. And this is some recent experiments with scallops and other things. And how much time I have? I have in the last few minutes, I'll talk about some of the work we're doing in agriculture. In agriculture, there's a lot of agrochemicals that are sprayed for crop protection, and this is a big challenge because farmers are sort of some of the most entrepreneurial people I've met. They want to try everything to make things work. And one of the issues is crop protection is so important. Otherwise, you have significant yield losses and so on. And this is amount of pesticides that are sprayed per year. Over 1 billion drops are sprayed in an acre, but we don't know where all these drops are going. And so spraying is kind of blind, and we spray and pray that things happen and your crops are protected. So as a result, there's a lot of overspraying, and one of the issues is actually a lot of leaves tend to be mildly or mostly hydrophobic, and you end up with a lot of drops actually coming off and leading to significant agricultural runoff. And here what you see is a result of that leading to contamination, drift, ending up in air, in our soils, and also at the same time, this is a huge market, right? So we've kind of tried to understand why this is the case, and this is looking at dynamics of drops impinging these kind of surfaces, and how can you get them to stick better so you can significantly cut this down, because this inefficiency is happening because drops are bouncing off of surfaces, though they add adjuvants or surfactants to these things. And the important thing is it's in this contact time. So the time it takes for surfactants to diffuse to the interface is way larger than the impact timescales. So long story short was we came up with many different techniques, and one of them here was using very thin nanoscopic cloaks that can be then deployed onto these droplets that allow immediate arrest and stiction. And these are all essentially plant-derived oils, and we have other things that we can use. And what we have seen is a significant reduction in the amount of pesticide use and so on. So we went to the farms, we tried this out to take this out, and we actually formed a company called AgZen to commercialize this. When we went to the farms, farmers have to deal with so many things. This is a boom sprayer. There is all kinds of parameters, spray height, droplet size, et cetera, that these people have to keep track of as this is happening. So the farmers had asked us, okay, this is all great, we want to use it. What do I know about my current coverage? How much of coverage am I getting? Because they all know coverage is the king in terms of crop protection. And so no one has measured this. No one knows where these drops are going. So we actually came up with an approach where we have we devised a tool which is, can someone click that? Can you click the top thing? So we devised a tool where you can do a bolt-on retrofit, and actually in line when the farmer is spraying, we can find out where these drops are landing, how many drops are there, and how much coverage they're getting. So if they're getting too fast, you can see that their coverage is obviously dropping if they're going too slow, and they can actually change what chemicals they're using, and we have a kind of a heat map of where they're doing sprays better and not. And the amazing thing here is to give you $1 billion back to farming in a year, all you need to do is 6% savings in these agrochemicals. And today we have shown that this is deployed now in 1 million acres, and we have shown that we can do 30 to 50% savings. So we are hoping that this will fundamentally change spraying and can really deliver value to the customer, to the farmer. That's all I have. Thanks.
I would like now to invite the speakers to come to the podium so that we can have the panel discussion at the end. So first of all, thank you very much to Kripa, Desirée, and Michael for their great talks. I think they were extremely instructive, and we all learn a lot. I've been told that every time you go to a talk at MIT, you need to learn something. And I feel like I learned so much. So you clearly showed us different type of innovation when it comes to having impact on climate at different level, right? Starting from the very basic science and how to design new materials to valorize waste, up to having a system level approach where you're really thinking of how to modify industries that are well entrenched in our life and how we can design new materials to be able to solve them, and how to retrofit environmental principles in the design of our innovation. And then, of course, with Kripa, we saw a technology among the others, technologies that start from the lab and then they go out and have impact in the real life and in the environment. And so the first question that I have to you, that I would like to ask you is, when you, at the end of the day for us always starts with a student or a postdoc in a lab, right? And an idea that has to be developed. So when you think about solving a problem for climate, how do you pick the technology? Like, you start from the solution that you find in the lab and then you go from the problem, or you try to do vice versa, or you integrate both?
Me first?
Yes.
I think both approaches. We're at an institute of technology, and so I think you can do both approaches. I think we're constantly looking out for solutions, and then I learned from my colleagues more depth about these problems. You have to do a lot of homework to really understand the climate challenges, problems, the scale. I learned a lot, actually, even just from listening to my colleagues here. So I'm going to punt. I'm going to say both. You do both.
Any other input?
Yeah, I think that for me lately, at least, I started out in my career as a geochemist and oceanographer, really tracking molecules and worrying very much about what the impact of that would ultimately be. And so lately, my approach is definitely to kind of look at global scale materials, fluxes, and say, what can somebody studying nanoscale processes really start to contribute in this space in a way that it ends up impacting that large scale operation, and then thinking about how you actually get that from the lab out into the economy. But the students are definitely a primary area of focus. What are they going to like? What is their ambition? What are their interests? Because you always want to make sure that's well aligned.
I'll just add to this that I think the key point for me is, ultimately to have that impact. What's sort of the business case here, and how do things scale, right? And as a result, sometimes you may have a great idea which can work in a small coupon sample that may not scale because of various constraints. So what are those constraints? How do you then debottleneck them? Is it a technology issue, or is it a supply chain issue, or what is it? And then once you know that, then you can create a really great project to address those. So it's the quest for how do things get deployed, and then what is the science that one needs to do to get there.
Awesome. And then when it comes to take a technology and try to transition out of the lab, what is really required is to have an ecosystem that help you and supports the PI in managing IP, managing the conflict of interest, managing innovation, managing the policies, getting the funds. And so I think that to some extent, the MIT.nano is a good community to start thinking about not only the preparation, the synthesis and the preparation, the characterization of the materials, but also to build a community within MIT that allows us to think carefully and critically how to spin out the technology. At the same time, though, the three of you from your talks have interacted with either governments or with venture capitalists, with the startup environments. And so you may have experienced challenges in taking a technology, working with governments and working with the ecosystem to try to take it out of the lab. And so what are your experiences, and how do you think I don't think there's a major recipe for success, particularly in climate tech, but what do you think are the challenges that you experience, and how you think a solution can be found to some of the challenges? This is a tough question, I know, so I want to give you some answers.
It's the perfect question for the two of you, actually. It's a tough question.
I could start if it's where maybe Kripa has many more startups than I do. I only have been through this twice, but I think there are a few failures in the way that the academic to startup path is ironed. MIT is by far, in a way, the best at it. And I've seen other models. We try to remove as many barriers as possible and yet they still exist. And a few that I guess I would highlight would be the mismatch of time scale and expectation in tough tech particularly. So climate technologies are hard, right? We're not talking about using software to program an app, to sell dating or love or food services online. Like, we know those will sell themselves. We're talking about really thin margin industries that the whole world relies on, that are the basis of our economy. And then we have to make the technology work on top of that, which is often very difficult. As you know, this 18 order of magnitude scaling is no small feat, literally and figuratively. And so that, I think, traditional venture capitalists, catalytic investors, financial strategic investors are typically not really aware of the time scale, and that can lead to perceived failures that actually criticize the entire industry or the entire idea. So I'll use algal biofuel maybe as an example. There are many. So I think that the timescale adjustment is really critically important. Nth cycle is a technology that came out of the carbon nanoscience that I did here at MIT as a graduate student. It's now, we opened the first domestic cobalt and nickel supply facility this year in Ohio. That was an incredibly proud moment. It's still incredibly challenging to have the struggle of working with mining companies versus battery companies versus different types of investors and managing all of those expectations and the timelines. And they're just not harmonized. And that's really what creates the lag, and it's a luxury we don't have. I think the second thing that's a real challenge is managing conflict of interest. I'm kind of naively, optimistic that we're all in this for the right reasons, and we want to see our technologies have the impact on the world. Not everybody is like that, right? So we have to have conflict of interest rules, of course. Some of them are structured in a way that once you spin out a company, you're no longer allowed to work on that technology. That doesn't make a lot of sense, to take somebody who spent a decade or their entire life thinking about a problem really deeply and say, and now you're no longer allowed to work on that in this capacity. We bring a lot to the table as professors. We're able to mobilize, scores of individuals, sometimes many more than that, and often many more than that. We shouldn't be eliminated from doing that because we had an idea that we wanted to see be not just the paper, but actually the product.
Oh, great. Those are points. Just to add to what Desirée said, I think in my journey I found, so first step was knowing your customer. Where are you going? And most of the times you may start with, that's my problem I'm solving, and you find yourself at a point where maybe that's not what is needed, and you have to then pivot or adjust. And or for example, on the topic that I just showed you, we had a solution for reducing agricultural sprays, but then the farmer wanted to know how much is actually on their leaves. So if we didn't listen to that, we wouldn't be in a place where we are today, because knowing that and taking that as an opportunity, we came up with a tool that tells them now how inefficient they are, and then we can come up with ways to then deploy what we've invented. And the other thing that also becomes useful is, when I did my first startup, I had a proof of product, which was a ketchup bottle, and people said, "Oh, this is great. I can see how this could be used." And then we went to the next, and then we had to scale from there. Well, it worked there, and we showed how we could do it. But scaling to making hundreds of bottles per minute, I did not even think of that. So it's huge manufacturing challenges there. So the next company I did, we started thinking about scale from the get-go, right? Doing that along with the science, and then you can see we deployed it here. And what that does is, as you keep doing that, you can reduce the risk for investors. And these are all very capital-intensive markets. So how can you get there fast, and how can you reduce the overall capex and opex as you go through this journey has been an important learning. And as you said, the capital availability is not infinite, right? So everyone has their own liquidity timelines and so on. So you need to have a return on investment. So how quickly could you start making money on the things is very, very important. You can't just say, okay, I'm going to do this for another 10 years in a startup, because then the startup won't exist, or the markets would have changed, or rules would have changed. And so keeping all that in mind and quickly getting to revenue is key to making this happen.
And a question that I have for Michael, and if somebody wants to submit questions, you can always use the QR code over there in case, but although we are running out of time. But you, Michael, have worked on carbon nanotubes for since I follow your research. And I think the trajectory that I saw for the use of carbon nanotubes, which have been extremely powerful, like as an example of nanotechnology, has been that many people have seen the potential, but then when it came to adoption, there was some skepticism, because there were many some concern about safety, for example. And although the community fought back and they presented cases, I think when it comes to use them in plants, you develop a very clever way to justify the use of carbon nanotubes through the plant sentinel model. So do you think that the question that I have is, how do you come up with the idea of the plant sentinel model?
to that, well, maybe it's a reminder. Maybe it's a reminder that the solutions to the problems we heard about today may come from inventions that don't exist yet. Actually, that we're still at an institute of technology, and we can still innovate and pull things out. I mean, I think I learn a lot from my colleagues with respect to innovation. These are some of the most creative people here we have at MIT. I would like to think we inspire each other. And I'll make a comment about the previous speaker, not to bring it down a notch, but I have my lab. We have more experience, I think, in licensing technology. We don't think about that as well. You can do a startup, or somebody can come and license technology, and I've always found that also to be an awkward process. That you're in this liminal space. Just because someone else now has the right to your patent, it doesn't mean all of that engineering know-how just magically transfers. We have to rely on our students, sometimes people that have already gone, and it is awkward, and there's conflict of interest. And I found that process could be streamlined a bit better. Sometimes a firm will hire you and your students as consultants for a little bit of time while you go and set up shop in their facility. I often think, maybe like my colleagues, sometimes a startup would have been better, a better vehicle. And so if there are people out from Sloan, or people that think on the policy side, we definitely need attention to that problem. I'm sorry, that was a little more into the weeds.
No, but
Yeah.
I think that's part of what we need to do as a body of faculty when it comes to, particularly when it comes to climate technology. It will require new rules of engagement to be able to bring these technologies out. The usual model that we see doesn't work for us. And so as the innovation enterprise and the research enterprise of MIT will change in the coming years, I think that our voice has to be more and more heard from the whole ecosystem of innovation when it comes to what it takes and what are the challenges and the opportunities to take this deep tech outside the lab. Thank you very much. I think our time is up.